Hey everyone, the presentation will be presented by myself and my friend Rajeshri. Here's a very quick flashback. Every 10 years or so, something big happens in mobile. New generation of mobile technology comes along. Each generation has set out to fix the flaws of its predecessor. GSM fixed the security weaknesses of analog telephony. 3G was meant to sort out GSM's lack of mobile data. And given it didn't much succeed, 4G was needed to finally make consuming data less of an unpleasant experience. Now, 5G is emerging ahead of the turn of a new decade and the next big change to hit mobile. But what's the problem that 5G is meant to fix? Amongst all the problem it is trying to fix, energy consumption and data rate needs no introduction. This paper presents recent advances in energy efficient networks and their application in 5G systems. So let's start. Energy efficiency. Why energy efficiency? Recently, energy cost and its contribution to global carbon dioxide emission are emerging as major concerns, which is a severe problem for cellular networks. Networks need to be energy focused on two fronts: reduced energy consumption of all network resources to lower the operational cost, and increased battery life to enable massive deployment of sensor networks. Energy efficiency, what is it? It is nothing but the cost of energy consumed to achieve spectral efficiency. And how about spectral efficiency? Well, spectrum is and it will remain a major challenge for the success and early rollout of 5G. We don't have enough spectrum in general, and 5G is a lot about optimizing the use of spectrum. Also, spectral efficiency doesn't necessarily imply energy efficiency, there can be a trade off. Just like a trade off between energy efficiency and time, energy efficiency and cost. We are interested in improving energy efficiency as well as spectral efficiency without compromising the user's quality of experience. Moving on, why do 5G systems even require this? To provide massive connections from various terminals, example Internet of Things, with diverse quality of requirements, 5G systems must have tremendous spectral and energy efficiency improvements simultaneously. While increasing the network capacity 1000-fold can be achieved by a large number of small cells, large-scale antennas, and much wider bandwidth in the millimeter wave bands, reducing energy consumption at the same time is still very challenging. The paper presents the following. We've already seen that CO2 emission and operational costs are important. Also, energy efficient transmission originates from energy constrained networks such as wireless sensor networks, ad hoc networks, and satellite communications, where wireless devices are powered by batteries that are not rechargeable or hard to recharge. With the recent explosively growing demand on mobile multimedia communications, the battery energy constraint has become a major concern for smartphones. This motivates optimization towards improving the energy efficiency of mobile devices. On the other hand, to reduce CO2 emission and support sustainable development, resource allocation towards improving the energy efficiency of networks has drawn considerable attention. In the early stage, the focus was minimizing the transmission power only, which is reasonable when the transmission power is dominant, such as in long range wireless communications. However, in short range transmissions, such as sensor networks and small cell cellular networks, the circuit power is comparable to the transmit power and it cannot be ignored. In short range transmission power directly related to the data rate and the circuit power should be carefully balanced to achieve high energy efficiency. Rajeshri will take over from this slide.
Spectral efficiency and energy efficiency relationship. The objectives of radio resource allocation can be classified as user-oriented and network-oriented. The user-oriented reflects the interests of individual users, including the quality of service requirements of a user and a battery power consumption. The network-oriented reflects the usage of network resources and collective measures. Spectral and energy efficiency are from network perspective and depend on the channel characteristics and system settings. Quality of service, on the other hand, is from the user perspective and relies on the features of sources and diverse traffic demands. Finding the spectral efficiency and energy efficiency relationship. It can be divided into two categories. One is to find the relationship directly from the capacity formula like the above two types, or you can find it out from the maximizing instantaneous energy efficiency. Besides analyzing how the optimal energy efficiency changes with the required spectral energy efficiency, how it changes with the quality of service requirement of each user has been investigated. In general, the spectral efficiency or energy efficiency relationship depends on the relative values of the transmit power and circuit power. If a system operates on the circuit power dominant region, maximizing spectral energy efficiency can also improve energy efficiency. If a system operates in a transmitted power dominated region, there will be a trade off between spectral efficiency and energy efficiency. Energy Energy efficient resource allocation. Since energy is directly related to the expenditure in operating a communication system while throughput brings revenue, a basic principle of energy efficient optimization is to maximize the energy efficiency without compromising the user experience or reducing the throughput of networks. Due to ubiquitous applications of real-time services such as video streaming, online gaming and mobile computing, which are all delay sensitive and power consuming, and also spectrum or energy efficient transmission subjective to quality of service requirements over wireless channel is important. To address these three performance metrics for resource allocation, one method is to maximize the energy efficiency of the network under the quality of service constraint imposed by the traffic. The resource allocation in this case can also be formulated as some sort of multi-criteria operation optimization. Four key criteria optimization such as objectives, functions, constraint, variables and algorithms. Functions. Network can be classified into capacity coverage limited, single or multi-cell and uplink or downlink transmission. In rural areas, energy efficiency is the ratio of average power consumption to the total coverage area. In urban areas, the traffic load is often high, hence energy efficiency is a ratio of overall number of bits transmitted to the energy consumed at a certain period of time. For uplink transmission, if battery energy is a concern, the energy consumption are from each user, and if reducing CO2 emission is the design goal, the energy consumption is from both base station and users. Constraints. Different services provides different quality of services like data rate, bit error rate and delay rate. All these finally depend on traffic model. They can be of two types, real time and best efforts. Both of these can be either full buffer or not. For real-time traffic without the full buffer, the quality of service constraints of the user are usually characterized as the average source rate and upper bound on the average delay, where the average delay includes both transmission and queuing delays. For non-real-time traffic such as best effort services, there is either no constraint or only a minimal throughput constraint. For delay-sensitive traffic, a more accurate constraint should be delay bound and its violation probability. Algorithms. The energy efficiency maximization problem belongs to a class of optimization problems called fractional problems, where the objective function is a ratio of two real valued functions. The ratio can be differentiable or discrete. When it is differentiable, energy efficiency is a pseudo concave and the optimal solution can be found from the KTT conditions and algorithms such as bisection algorithms or multi-level water filling algorithms. Device to device communication. With the growing trend of proximity based applications such as peer to peer, file sharing, local multicasting, and advertising, D2D communications have been proposed to improve local flexibility and network throughput and to support public safety servers. Advantages are proximity gain, reuse gain, hop gain, network spectral efficiency, device energy efficiency. Through proper mode selection, energy efficiency of both devices and the network can be significantly improved.
Now, let's talk about small cells. What are the advantages? Low power, low cost base stations. It can be densely deployed to get high data rates. Frequency reuse can improve spectral efficiency significantly, etc. Sure, small cells are far lower powered than macro cells, but a network with huge number of them dotted around will still need more energy to run than one without. Some of the challenges are, since small cells in 5G will be much denser than 4G, for hotspot coverage, managing interference while considering the spectral and energy efficiency target will be challenging. Because of their reduced size, small cells have a much reduced range compared to their bigger siblings. That means there's a potential challenge with handover. If you are in a car speeding through town, you could be passing through several small cells, and with each handover, you risk packet loss or distortion. Now, that's a royal pain in the ass if you're in the middle of a call. Traditionally, energy efficiency was defined as data rate upon power consumption. However, in some projects, both the power per unit area and per bit energy consumption have been used as metrics for system level evaluation, which is often called the network energy efficiency. If users' quality of service is to be taken into account, then redefining energy efficiency is required, and following two problems need to be considered: net energy efficiency and end to end delay. Net energy efficiency is given by the formula shown above, and end to end delay determines your quality of service. However, very little is known on how to model energy efficiency with respect to end-to-end delay, keeping in mind that both of these need to be redefined, keeping the user's quality of service into account. Energy efficiency for new network architectures and waveforms. 5G network will support multiple radio access technologies for co-site deployment, which provides a potential for energy saving. CRAN, which is also known as Cloud Radio Access Network, which was first introduced by the China Mobile Research Institute in 2010, it's a new radio access architecture for future mobile network infrastructure. With such a new architecture, much higher utilization efficiency of processing resources can be achieved by sharing the baseband unit pool among large number of cells, reducing power consumption for air conditioners by reducing number of sites, and reduce transmission power due to the short distance between the users and the remote radio head. By using a virtual baseband transceiver switching pool, multi-cell cooperative baseband signal processing, and dynamic cell load balancing, CRAN has been verified to be more energy efficient than conventional RAN in field trials. However, to improve the energy efficiency of the entire network, some problems still exist. Energy efficiency in massive MIMO. MIMO is another technology, a potential candidate for millimeter wave band, which is likely to arrive in a big way with 5G. Rather than having a single antenna in the receiver and one in the transmitter, MIMO, which stands for multiple input, multiple output, envisages a scenario where both set of equipments have tens or even 100 antennas or more. That translates into better data rates for users and helps with both spectral and energy efficiency for operators. But there is a challenge: designing a scheme that is energy efficient. Take a look at the following two issues. Case 1. Requirement is an adequate energy consumption model. Why is it required? Because it is directly related to your objective function. Now, frequency band decide the power model of RF front-end devices. Hence, it is hard to measure and model the energy efficiency of a massive MIMO system. And impact of the hardware impairment on energy efficiency in MIMO systems hasn't been evaluated yet. Energy efficiency in massive MIMO systems in heterogeneous networks. Given an area, it can be covered by a massive MIMO cell or a set of small cells. From the perspective of energy efficiency, deployment of massive MIMO and heterogeneous networks for the same coverage is still being debated. Sleep mode control in heterogeneous networks can provide more flexibility and higher energy efficiency for a large number of small cells, while a massive MIMO cell performs better than a small number of small cells due to its array gain. And thus, energy efficient massive MIMO systems in heterogeneous networks are worth further study. Interference among D2D links and between cellular and D2D links is a problem in D2D communications. A solution would require significant signaling overhead, which sometimes outweighs the advantages. The solution is nothing but energy efficient device to device spectrum sensing. But if enhanced with cognitive radio technology, user equipment can identify the portion of the licensed spectrum that is unused locally through spectrum sensing and opportunistically reusing the resource for D2D communications without even introducing interference or additional signaling overhead to the existing cellular network. Energy efficient resource allocation in a multi-cell scenario. The bad news here is it's more complicated compared to a single cell. Why is it? Because a coordination between neighboring base stations is required to deal with channel feedback, managing mobility, and handover issues. Good news is it consumes less energy. So, coming to the conclusion part. This article has presented a comprehensive survey on recent advances in energy efficient wireless networks in the past decade and identified emerging challenges for potential applications in 5G cellular networks. D2D, small cells, massive MIMO are some of the promising solutions, but they do come with their own challenges. Energy efficient resource allocation has been addressed from the optimization perspective. Many open issues in designing energy efficient 5G systems such as massive MIMO and D2D have been provided. So, while 1 Gbps speed is a baseline for 5G, multi-gigabits is the aim. Consumers, according to the industry types, should have the feeling that they always have all the capacity and speed they need, however much data they are using and wherever they are. If 5G networks are built well, there will be no need to append mobile technology every decade, just update it bit by bit as new needs and technology will arise.